Okay, well, Atwood machine, the suspended mass and mass on the incline here, suspended mass and mass on a level here. Now, level's just an incline with zero angle. First, the Atwood machine, just to summarize what we talked about for 10 minutes or so. First of all, we assume the pulley to be frictionless, at least for now. Not that hard to work friction into it. Keep it simple at the beginning. Pulley's frictionless and the string is light, meaning it has negligible mass. So it contributes nothing to the mass of the system. Okay? Well, in that case, the string tension has to be uniform, because if, well, it comes down to the tension here and here has to be the same. Tension here and here has to be the same. And if the pulley's frictionless, there's no tension here. And pulley's frictionless and light, meaning it has no significant mass. Ultimately, no significant moment of inertia, which is what causes acceleration, or what's related to, what's most nicely related to the acceleration of a rotating object. And we haven't talked about coefficient, moment of inertia. But if the pulley's light, then basically the mass of the pulley has no effect on the motion of the system, same as the mass of the string having no effect. Okay? Under these circumstances, string tension has to be uniform. And in that case, let's assume that M1 and M2 are unequal with M1 greater. Then we know, of course, that this system is going to accelerate in the direction where M2 goes downward, M1 goes downward, M2 goes upward, right? And the magnitudes of the acceleration will be the same, assuming the string isn't stretching. Okay. We could then isolate the two masses, and we could say, okay, we have each mass has a tension acting upward and gravity acting downward. Well, if that's the case, then if we draw the tension and the M1G, knowing that this mass accelerates downward, the tension vector has to be shorter than the weight vector. If they were of equal length, then there'd be zero net force on the object, they'd have no acceleration. Okay? If mass 1 is greater than mass 2, we know it accelerates this way, which means that this force has to be less in magnitude than this force, so you have a non-zero downward result. Similarly, the tension force has to be greater in magnitude than the weight force on the second object, because if we put these two vectors together, this one being shorter than this, we get a net vector upward. Fairly simple idea. There's another way to analyze this system, to say that the net force on this rotational system is, if we take the counterclockwise direction to be positive, the net force would be M1G minus M2G. Difference in the two weight forces. And in the positive direction, the direction toward M1, whether that be positive or negative. Okay, the direction toward the greater, the rotational direction towards the greater, where the rotational direction is, we can take it to be the rotation of the pulley. Okay, when we do more with rotational motion, there's another way to conceptualize that. Then you have an acceleration that's just M1G minus M2G, this force minus this force, divided by the total mass, right? So you have also the possibility where you don't break these apart, That says ALT, alternative interpretation. So one interpretation is you isolate the two masses. Another interpretation is you just find the net force by subtracting, okay? And divide by the total mass, that gives you the acceleration. If you do this analysis, you have to have the same acceleration both times. It gives you two simultaneous equations. If you solve this, you get the acceleration right away, and then you can take either of these pictures and find the tension. Because once you know the acceleration, you know the gravity, you know the net force, and so forth. Okay, well, maybe I shouldn't even mention that at this point, so it doesn't make sense to you. Just kind of store it away, come back to it. We'll talk about it later too. Okay, so let's take this case. And the only question I want to ask about this is, where are the vectors? What are the directions of the vectors? There are two possible results. There are two possible answers to the question. One, you got the normal force call this M1, call this M2. You got the normal force up, M1G down. You have the tension, which is to the right in all cases. And then, depending on which is greater, M1 or M2, you have the frictional force. Okay? Actually, I might take that back. What I was about to say applies up here, it doesn't apply down here, so forget what I just said. Okay, this is it. Except, of course, you have a frictional force. And there's your picture. Now, this assumes that the mass M1 is not moving in this direction. It's possible for M1 to be moving in this direction, like I give M1 a shove. So that's going to make M1 go this way and M2 pull up, right? But because of the tension force, eventually things are going to come to rest. Then it'll either stay at rest depending on the coefficient of friction, and that's something you worry about a little bit later, and you'll encounter it. Or it's going to turn around and start accelerating back this way. Okay? So I'm just going to say now, this assumes that M1 is not moving to the left, because if it is, then the friction is going to be to the right, because friction opposes your motion. Okay? Now, as I give this thing a shove to the right, I know that friction is resisting me along with the tension. When I let go, that friction doesn't stop being exerted in this direction until the thing stops. At which point, now the friction is suddenly in this direction. And that continues whether the thing remains stationary due to static friction or turns around due to kinetic friction. Due to static friction not being sufficient to hold it back against this mass. again, words of wisdom that you might want to think about as you go through these things, okay? Trying to give you a first idea, get your brain working on these things, and your homework assignment should help clarify everything. Okay, in this case, I'll actually draw the forces on the diagram. I kind of didn't have room over here, but you have, well, this is M1. This is M2. Okay, so you have M1G. Is that normal force? You have tension. And you have a frictional force. I'm going to do it this way. Is your frictional force this way? You're not sure, because it kind of depends on which mass is bigger and on the angle, okay? Relative masses and the angle. And also whether you've given it a push in the direction it doesn't want to go in. So if it's already moving upward, then the friction is definitely here, no matter what. If it's already moving downward, then the friction is this way, no matter what. If this mass is a whole lot bigger than this one, and the angle is significant, then the whole thing's going to want to go this way anyhow. And friction will be this way. So you don't know which direction friction acts in, and doggone it. Look at my orange chalk. What do I do with it? Oh. Glad somebody can keep track, because I sure can't. Okay. A friction can't be in both directions at the same time. Now, in the motion of the object, friction could change direction. If the thing changes its direction of motion, then certainly friction changes direction. If it's moving and comes to rest and stays that way because static friction is greater than kinetic friction, then friction's again going to reverse its direction. Friction can. Pretty sure what I said is right. Anyhow, it's something you want to think about. So you don't know whether friction's in this direction or this direction. Okay? And you have to consider the motion of the system, the relative forces, and everything. So you've got to analyze a bunch of stuff. Now, in both of these cases, of course, you've got a free body diagram for mass M2, right? You can isolate mass M2. So let's just say M1 is regarded as being at this point. In either of these cases, you have M2G and the tension. And until you have more information, especially in this case, you don't know whether the tension's bigger than M2G or less. Or maybe equal. If the thing is stationary, they're going to be equal, right? Well, I actually think, yeah, stationary, they're going to be equal. Okay, because if this thing's not accelerating, these are the only forces acting on it. They've got to add up to zero, meaning they've got to be equal. Okay. Another bit of extraneous information, I'll just say it now, but I'll write it down and say it again. this is the equation you always want to write. Okay, not necessarily sum of the y forces is zero, but just sum of the forces is zero if the thing is in equilibrium. You don't have to say these forces are equal to these forces, or equal and opposite to these forces. You just write all the forces, sum of all the forces on one side of the equation, okay? And then if it's in equilibrium, equal to zero. Not in equilibrium, well then hopefully it's equilibrium in either the x or y direction. And that'll usually be the case. Okay, so let's talk about free fall and bank curves and vertical circles and such.